Okay, so it's already late, 3 minutes. So let me introduce today's speaker, Dr. Hoon Jang, the new member of Sequest. He got the PhD from Professor Horati. So he's a well-known expert for supergravity. So today, Hoon will talk about supergravity cosmology.
Yes, thank you for the introduction. So this time, I'm going to talk about supergravity cosmology. Basically, supergravity can be obtained by gazing supersymmetry, and also it can be obtained from low energy effective descriptions of superstring theory, which is the most promising candidate of quantum gravity. This is my content. So I will start with inflation story, and then I will go over a brief review of supersymmetry, and then we're gonna talk about some tense calculus of general case theory to construct the conformal supergravity. In that constructions, it's very important to utilize a new special concept which is called gauge equivalence program, which would be the core at construction conformal supergravity. And then I will show you some of the details about the constructions, and finally I will talk about how we can describe the slower inflation in the context of conformal supergravity. Okay. Inflations. So I would like to start with the very famous observation about the expansion of our universe. So this is the distance redshift Hubble diagram. So the vertical axis is the distance modulus, just you can consider it just distance from the observer to the galaxies or the other celestial object. And then the horizontal axis is a redshift, which is defined as the change in wavelengths of light emitted from the celestial objects like galaxies and other stars. In this case, it's very well known that our universe space-time can be described in the Friedmann-Lenders-Roberts-Walker space-time metric. But just the point here is that just you can remember that the universe expands due to the evidence of these guys. And then there's other evidence about our universe. Actually, the standard model is not enough to describe our universe, because in addition to the expansion, actually there are still some energy budget of the universe issues. So our universe has some energy budget, which is divided into some components. So there's going to be some baryon matter portions and also some coarse dark matter portions. Actually, the baryon matter is going to be the 5%, just around the 5% of the whole of the total energy budget. And then the other, the dark matter will retake the 25%. Just the other 70% comes from dark energy. So this is the evidence from the Planck missions in 2018. So just please keep in mind that just the standard model is not sufficient up to date. So the other observation can tell you some very interesting features of the universe, which is called the cosmic microwave background photons. So the CMB photons, or the CMB light, actually is defined as the light that was generated from the primordial plasma in our early universe, or right after Big Bang. So the observation says that the CMB temperature is around 2.7 Kelvin degree. So the point here is that there must be some summer equilibrium of the primordial plasma, because this means that wherever we see, actually we're gonna see some same temperature photons. So that means there must be some path in which the photons could interact with each other up to some summer equilibrium. So which means that actually there was some proper quarter contact. The quarter contact, just you can consider it like the place in the past where the photons interacted with each other. But before talking about inflation error, the people talked about some controversy about the CMB photons. So the problem is this. So just forget about the bottom half of the graph. So at first, people thought that actually the people didn't know how they could interact with each other in the past, because of this space-time diagram. You know, just the projectile direction is just the spatial dimension, and the vertical direction is the time dimensions. So here you can see that there's two different independent quarter contact here. So basically, there's no region about the same temperature of these two different photons. But we have the observation, right? So one of the person who studied this kind of cosmology, which is just Alan Guth in MIT, proposed very interesting scenario, which is called inflation. So during inflation, actually, there can be some quarter contact here, just a single quarter contact. So actually, the CMB photons could interact within this quarter contact, and then they goes to the other direction, just shown here. So this kind of problems is called the horizon problem. So actually, the inflation can give us the essential quarter contact so that it can solve the horizon problem. So in fact, there are many scenarios about the inflation scenarios, but just I would like to emphasize that among the possible inflationary scenarios, actually the Stravinsky type inflation is going to be the most promising candidate of our universe inflations because of this data from the Planck missions. So this is just a brief review of inflation dynamics. So in fact, actually, this ratio is defined by the P over rho. The P is the pressure and the rho is energy density. In fact, matter particles has the vanishing value of the W. But for inflation, we need some negative value here. So which means that we need another type of matter, which is called improtons. The improtons can be described naturally by the single scalar field, Lagrangian here. So this is actually this has the following energy density and the pressure, and the Friedmann equation is defined by the Einstein field equations in the FRW metric. And then also we need some continuity equation here. So by combining these two, we can obtain the equation of motions of improton. So this is the second derivative equations. And then to make this negative value of omega, we need some special approximation, which is called slower approximation. In this region, in this limit, we can realize the negative value here. You know, there's some components here, so just you can easily guess how things work here. So you can consider this equation as a Newtonian dynamics, just F equal ma. So this is the acceleration of the field value, and this is going to be the conservative force, and this is called the Hubble friction. So in the end, the Hubble friction will prevent the improton rollings from rolling fast, but in this slowing approximations, only in this approximation, actually the improton can generate the inflationary error. But if this approximation limit is violated at some point, then the inflation will end, and then the improton will go to the true vacuum, and then with oscillating, and then the improton energy will be transferred to the formation of standard model particles during reheating error, so that the standard model spectra could be generated from the plasma.
So when you say Stravinsky model R square potential, actually, so you are rewriting the higher curvature term in terms of some scalar degrees, and they will produce potential or something like that. Is that what you mean? When you say potential, R square is not potential itself, right? So you are rewriting in terms of the scalars. Right?
Yeah, sure. So I plus R scalar model can be equivalent to some scalar theory with the linear curvature. Yeah.
And how does the shape look like?
The Stravinsky potential. Yeah. This is the Stravinsky type potential. Yeah. So there's going to be some flat directions here, and there's some quadratic region. Yeah.
or other cases like a phi squared, phi to the n, such
yeah.
a monomial type.
Mhm.
So you are talking about some kind of chaotic impression or something.
In this talk, I will focus on the Stravinsky inflationary potential. So in the end, I will explain how to construct this kind of potential in the supergravity language. Yeah. So the other data tell us that basically the isocoverture perturbation is quite less favored, which means that the inflation should be made by a single field degree of freedom. The isocoverture perturbation means that just let's imagine we have a lot of scalar degree of freedoms at first. Then we may have some scalar potential that correspond to the degrees. Then actually the scalar potential is going to be some multi-dimensional type. But in this case, since the flat direction contributed to generation of inflations, so if we have some many flat directions in the field degree of freedoms, then which means that we're gonna get some infinitely many trajectories of inflations. So in this case, we don't know how the effectively single field inflation could be made. So the isocoverture perturbation is just oscillations of the other scalar degree freedoms, but in Platon. But in this case, the scalar potential, the quadratic potential, will not be the case whose mass value is not greater than the Hubble mass. If the other scalar field has a less mass, less than Hubble mass, then that scalar can generate inflation. But if the scalar field can be sufficiently heavier than the Hubble mass, then that scalar will not contribute to the inflations. So this is going to be some strategy to realize the single field inflation in our story. Okay, so
I'm a little bit confused. So I do understand that if we have too many scalars, like low Hubble mass scalars you mentioned, we have too many undetermined parameters. So
Yes.
we may not know, we may not make actual progress in the direction. But how can we say that single field inflation is preferred by that? I mean, you know, am I making sense? I mean, I feel like I don't know why it is preferred, a single field inflation.
due to the data. Yeah.
So you're saying if we have too many scalar fields that may contribute to the inflation scenario you mentioned,
Yes.
then we in some sense we can make our theoretical expectation to match the data in any case, right? We have too many parameters. Are you saying something like this?
Yeah.
What was the outcome? The table?
This is the isocoverture perturbation observable. This is the idea value.
How is it defined?
The alpha minus 1. Yeah.
What's the definition?
The intention?
Definition.
The definition is this is related to how the scalars can fluctuate in the direction particle to the inflationary trajectory. So if these values if this value is very small, then which means that such oscillation patterns will happen within very short regions. So just average. So for example, let's say this is the inflation trajectory, and this direction can be some implanted direction, for example, but also we may have some many scalar degree of freedom, say psi or more chi. So in some sense, this scalar field can also have some scalar potential, something like that, right? But if the scalar potential may have this kind of case, then the oscillations in the psi directions may be large. But if the psi particle has very massive value, then the corresponding scalar potential will look like some steep quadratic potential. In this case, the oscillation will be very small. So if the corresponding mass is greater than the Hubble mass, then actually in this direction, the inflation cannot happen. So alpha minus 1 is the corresponding observable, and the details of the definition kind of very complicated. Yeah, that's related to the CMB observable. Yeah. Actually, I don't know much about the details of this observable because it is related to some numerical cosmology things. Yeah. But the thing is, actually, this data says that the single field inflation is going to be more frequent. So that's the reason why we care about the single field inflation scenario nowadays.
Many people still discuss multi-field.
Yeah, but noise speed inflations are less favored in many communities. Yeah, especially for high series. Yeah, due to the reason. Yeah.
Your argument propels that what is single field is light field is single.
Yeah, right field. Yeah, right scalar is the unit. Yeah. So
curvature is entropy fluctuation.
yes, entropy fluctuation. Yeah.
So alpha should be defined in that way.
Yeah, sure. Yeah. Yeah. And okay. I need to speed up. Okay, then the next is supersymmetry. So supersymmetry is just a symmetry that can connect the bordons and fermions in a single multiplet. So there's some supersymmetry algebra here, and these Q operators can
끝까지 다 먹어. 너도 잘 안 먹어가지고.
and rewrite all the symmetric algebras, and then we can consider the right constraint in this form. So in this way, actually, we can get consistent symmetric algebras. So for example, in the case of the moment operator, actually we get there's no some additional part, and also the curvature terms that correspond to the momentum symmetry must vanish. In fact, this constraint will determine the value of the spin connection gauge field. So the spin connection gauge field is no longer independent, but some dependent field. So, and then in this case, actually in this case, you can think that the transformation of this curvature will not be zero due to the transformation, the non-vanishing transformation of this guy. So in the end, after this, we need to put these guys, and then by considering this additional transformation of spin connection field, so we can get the right expression of the next symmetric algebra of this type. But in this steps, actually, we don't have to worry about this additional part. So this is kind of complicated, but just you can just ignore, yeah, because it's not a big deal in this story. So I will talk about the gauge equivalence program. So what is this? Just let's start with the projection of massive vector field. Just this is the user Maxwell term, and then there's some mass term here of vector particle. Then we may ask, can we have some gauge symmetry with this type? No, for now. Then how can we realize it? Is it possible? Sure. Yeah, we can do through the so-called the Supergravity tree. So I'll introduce Supergravity tree. First, we need to define a full symmetry, including some extra symmetry for the relevant field degree freedom. So let's say I would like to add some symmetry of that vector particle with respect to some scalar gauge functions. And then just we need to choose some compensator. The compensator is a field that can compensate the remnant change, the remnant gauge transformation of the other fields. For example, we can consider some scalar field A, and then the A will transform in this way. Then we can construct the invariant interaction. So here we just define the covariant derivative in this way, and it's automatically give us that actually this is zero under the transformations, so that the invariant actions can be written in this way. Then the interesting features arise here. If we gauge fix the unwanted symmetry, this guy, in this way, or if we take just field redefinition without considering gauge fixing, in this way, actually they can give us the same Lagrangian, So basically, the gauge fix theory can be equivalent to the field redefinition field theory. So Supergravity trick enables to construct gauge equivalence theories. So, just keeping these things in mind, actually, we can proceed some constructions of conformal supergravity. The conformal supergravity start with some Poincare symmetry. The Poincare symmetry consists of the space-time transformation and rotation. And then we can add some conformal group, which is the dilatation and special conformal transformations.
Excuse me? So you extend by adding some auxiliary field to restore the symmetry.
Yes.
So if you fix a gauge, then the additional auxiliary field gauge away, so which is reduced to the original theory. So which means that the original theory is nothing but the gauge invariant formulation of gauge non-invariant theory. So what is the motivation to?
Yeah. The motivation comes from the fact that this kind of construction will give you more convenient computation. Yeah, convenient computations. So actually, yeah, I will tell you that this kind of formulation is more convenient in some sense. So
you choose arbitrary gauge.
yes, yes,
In that sense, convenient.
yeah.
Even if you choose this gauge large A equals 0, we should not forget the equation motion of that field effect. And that gives you additional constraint. So the theory should not be the same as.
Yeah. That's the decompose. That's the so-called decomposition result. Yeah, actually. Yeah, the decomposition loss means the result after gauge fixing. So you're right. So getting back to the story of conformal supergravity. In addition to conformal group, and we may consider some supersymmetry, right? Then these guys is going to be called the superconformal symmetry. But in this case, the superconformal symmetry is defined the Poincare and some conformal groups and the user supersymmetry and another type of supersymmetry, which is called S-SUGI. The S-SUGI means that when you compute the commutation relations between the conformal operators and the user Q supersymmetry operators, then you will get a new type of supersymmetry operators. So that you need a new operator that corresponds to the supersymmetry result. And then by gazing, you can you're going to get some conformal supergravity, because the conformal supergravity means just the local superconformal. The local means the gazing. And by gaze fixing some unwanted symmetries, we can get the targeted theory, which is the Poincare supergravity. So actually, one may ask what's the pros and cons of this formulation. In fact, when you construct.
So that chiral you run in the superconformal, how does it act on the Q-SUGI and the S-SUGI?
This and this.
Yes. So chiral U1 acts only Q-SUGI.
Yeah. The chiral U1 symmetry can have some commutation relation between these guys.
So S-SUGI also carries some chiral U1 charm.
Yeah. And actually, the chiral charges will be positive in the case of the QCs. Yeah. So let me ask then what's the pros and cons of this formulation? Actually, this formulation is called the superconformal formalism. In fact, there are two formalisms in constructing conformal supergravity. The first one is the user way, which is called the superspace formulation, the superspace formalism, and the other option is the superconformal formalism. Actually, in superspace formalism, we have to worry about many things during the computations. Actually, we need to do some very complicated rescaling to diagonalize the relevant field degree freedoms. But in this case, and then the conformal supergravity can be defined with different auxiliary type, the auxiliary field. So which means that there may be different types of conformal supergravity theories according to the auxiliary field of interest. But in superspace formalism, it's not possible to relate the different theories with different auxiliary field. But in superconformal formalism, it's possible to relate the different auxiliary theories. So that's the another, yeah.
So I'm just wondering, in the end, are you going to break supersymmetry?
Yes, yes, of course, of course. I want to get some standard model particle spectra. Yeah, so we need to kill the unnecessary superparticles in the end. Yeah.
Soft supergravity.
Mhm.
Soft supergravity.
Right.
Soft breaking.
So, yeah, there's, yeah, I will consider soft breaking in the end. Yeah. Okay, so just you can enjoy the structure. So actually, just it's not it doesn't matter about this for now, but just I want to show you some how these operators can have the corresponding computation algebras. So it seems like a little bit complicated. So the strategy is this: the superconformal multiplet can be defined as a supermultiplet by imposing this condition. Actually, this means that the multiplet will not transform under the S-SUSY and the special conformal transformation. So if you so in fact the component field of the superfield, the pi, can be generated by acting the supersymmetry operators several times in this way. So actually, this if the lowest component of pi is scalar, then this is going to be some fermion, and this is another scalar, and this is the yeah, this is yeah, this is another spinner, and this is another vector, etc. So in this case, if we act some S-SUSY of Q pi, then due to the computational relation, we can rewrite these things in this way, and actually using the computational relation between S and Q, we can re-express these guys in the following way. The M is the local rank transformation, dilatations, and the chiral-Johan transformation. But in this case, you know, actually we only care about the descendant field with respect to the Q operators for only pi. But here there's S pi. This is a new field, not just pi. So we need to impose the the original field does not transform under the S2G. So from this condition, we can get these guys. But the thing is that in this way, we can define the needed all the transformations of the component of some superfield. So this is just a table of the right bichiral weight table, but it doesn't matter now. Okay, so this is the structure. So the supercomponent multiplet is basically defined some 7 components. So this is the scalar, spinor, scalar, vector, spinor, scalar. So just by taking advantage of the computation relations, actually we can determine all the other components of the supercomponent multiplet and their transformations properties. This is the point. So this is the kind of formula to find some invariant actions. So in conformal supergravity, actually we have this kind of constraint. From this constraint, actually the other some of the gauge fields will be dependent fields, not independent. So here you can see that there's some curvature terms here. So in the end, I would like to tell you that the space-time curvature, here realize in the stage of this dependent field value. So here you can see that there's some curvature terms and some fermionic interaction. So in the end, we will take some gauge fixing conditions to get some Einstein primed gravity from the conformal supergravity. So this is the most general Lagrangian picture. So this is the conformal supergravity Lagrangian. So you can easily get all the spectrum of the conformal supergravity in a convenient way in this superconformal formulation. Basically, this is the another terms. So basically, it's a monster Lagrangian. So yes.
Conformal supergravity.
Mhm.
Is it reduced to conformal gravity or just Einstein?
It's gonna be Einstein gravity in the end.
Not related to conformal gravity.
Yes. In this setup, the conformal symmetry is gonna be extra symmetry will kill. Yeah.
Extra.
Yeah. The conformal symmetry will not be physical. Yeah. Just like fake symmetry.
How is it going to be broken?
Yeah, just by gauge fixing. Yeah. By taking the proper gauge fixing conditions.
So could you remind me again, so the supergravity Lagrangian, only the bosonic part.
Mhm.
How does it look like? Could you tell us?
The bosonic part.
Yes.
Okay. So yeah. Here, this is the total contributions in conformal supergravity.
What is capital N?
The capital N comes from the
Simply scalar or what? I don't know the. Just
yeah. Just scalar function. Yeah, some general function of a scalar field.
And then in terms of bosonic part,
Mm-hmm.
the
bosonic part.
So there's a n times r.
Mm-hmm.
Then what else? What's the v at the end?
V is the potential. These guys.
N is constant or scalar?
The n is the general function of scalar field. Yeah, scalar field.
with anti-gravity protection.
Yes.
Non-minimal theory.
Yeah, in general, like just Jordan frame. Yeah. And also, so this is the spin zero kinetic term. This is a spin half kinetic term. And this is the spin one kinetic terms. And this is the finite supergravity scalar potential. You see, actually in supergravity, the scalar, the form of scalar potential can be determined in this way.
So in addition to the top line, equation 9, the action, then we do have to add equation 10, which is a scalar.
Yes.
Also capital I and the J bar, the index.
Capital
In the equation 10.
equation 10. I. The I and J bar means the index of the several scalar field.
How many?
Oh, it can be any. Yeah.
You are starting from 10 and come down to 4, or what is the dimension you are talking?
This is the field space dimension. This is X means the scalar field.
Scalar field.
Yes.
You are restricting to 4 dimensions.
This is the space-time dimension is 4.
4.
Yes. And the field space
I
dimension can be any.
I see it can be anything.
Yes. Yes.
Okay, and the Gij is a function of X.
The Gij is defined by the Taylor metric.
Okay,
The
good.
N and yes, this is the bar means the complex conjugate.
I am.
Yes, yeah. So basically the X, the complex scalar field is the conjugate.
And then L1 part. So in front of the F square, what is the real small f AG? What is the?
This guy. This is defined. This is defined as the gauge function. Actually the gauge kinetic functions. Yeah. So this
Is it constant or is it function?
function in general.
Function of what? Some
Function of a scalar field. But in this case, this function is going to be holomorphic function.
Okay.
Yes.
Function of not n but x.
Mm-hmm.
So it's a function of x, xi.
Function of x. Yes. Sure.
타입으로 있습니다. 대자 사건.
And then the potential torsion is that depending on the choice of the W, essentially.
Yeah, superpotentials and some gauge symmetry contributions.
Also.
Yeah, only if we have some gauge symmetries, then we can define the D-term potential here. If we have any gauge symmetries, then this term will be gone.
I was wondering, is this in the end, can you get to the zero vacuum? Like, do you have some uplifting mechanisms?
Yeah, but I will talk about in the end, yeah. So
and in the scalar potential.
yeah, sure. Yeah, in general, the N will be defined by some. Yeah.
N is a function of xi and xi.
Yeah. So basically, this is the N is just scalar potential, but the detailed form is going to be something like this. Something like I xi bar.
Exponential minus scalar potential.
Yeah.
Actually,
Yeah.
scalar potential will determine functional form of N.
Yes.
Okay, good.
Yes, that's the point. Yeah. Okay. So we see there's a lot of terms, but it's quite predictive. So this is advantage of conformal supergravity. And this is the other terms. Yeah, the high order
And the
interaction terms.
gauge field should be always only U1 or it's a.
Just you can consider abelian gauge groups and the non-abelian types. Yeah.
Any non-abelian or?
Yeah, no, any.
And
Yeah, any. In principle, any.
Do you have a super space simple expression?
Actually, in superspace, we can get the same Lagrangian spectrum, but it's necessary to apply some complicated rescalings to match between them.
You don't derive this from super space formalism?
Yeah, we don't have to.
You can derive the
Yeah.
final answer anyway, but the point is you can basically use the same formalism as a global feature in this supercomputer.
Yeah. Basically, in superspace, actually, in superspace formalism, the corresponding conformal supergravity is going to be some theory defined on superspace. So actually, we need to consider some proper super pure brines and etc. But in this case, we don't have to worry about any superspace things. Just we can start with just the normal space-time manifold, and just by applying some supersymmetry algebra, commutation relation algebras, we can construct these things. So that's the difference.
Model is more or less determined once scalar potential is given, and also d-term potential.
Yes.
And is d-term potential related to some Suji breaking or no?
It's related. Yeah. So I will talk about things in the end. So this is the gauge fixing conditions. So by gauge fixing these guys, just I need to speed up. So we have 4 gauge fixing conditions. So in the end, the physical action can be described in this form. So we have some Einstein-Hilbert actions, and the other Bordering and Fermionic interactions. So the details of the scalar potential forms is this. So this is the user superpotential, and this is the this is defined by this guy, and the K is the scalar potential of the n definition here. So in the end, also the masses of all the fields can be determined by the superpotential and the scalar potential as well. So the thing is that we can have the Einstein-Hilbert actions by gauge fixing these guys easily. And then the supersymmetric breaking, the Suji breaking is related to the following. Actually, here the superpotential terms here, and there's some momentum map functions. The momentum map function is defined by these guys. So actually, this is the killing vector, the killing vector of gauge symmetry, and this is the scalar potential. So and then these additional constants, which is called the Fayette Ilioporos terms, which can be defined only in the case of gauged R symmetry. But I will omit the detail of R symmetry story. But the point here is that the Suji breaking is governed by the value of a superpotential and the moment map of gauge symmetry. And then there's some superheat effects and supersymmetric breaking story, but just I think I need to speed up, so I will I skip it. So the last story is the inflation in conformal supergraph. Okay, so at first I would like to introduce a brief review of effective field theory concept. So in the case of the non-renormalizable series, actually there's going to be some higher order interaction terms, which means higher mass dimension operators. So in this case, we need to keep some accuracy of the amplitude, corresponding amplitude, with respect to some special cutoff. Then we need to require the Wilson coefficient, which is called, this is called Wilson coefficient. We need to require the Wilson coefficients must be well suppressed with respect to the cutoff of interest. So only in this case we can describe the effective field theory without any trouble with the counter terms about the renormalization. So the point here is that we're going to get some constraint from the effective field theory perspective. So this is the work I've done with my PhD advisor, Massimo Forti at New York University. Actually, the details of the model is quite complicated to explain, but just I would like to tell you that by using this kind of proposal, we were able to succeed in realizing some inflationary model and then some mass spectra of standard model particle. But before going into this story, just I would like to emphasize that we find some special relation of the cutoff of the series. So this is kind of surprising fact. Our theory has the cutoff scale at some 10 to the minus 2.5 amp Planck, which is equivalent to the string mass scale and also the grand unified theory scale.
How did you estimate that?
Yeah, from the effective field theory constraint. Yeah, from here we can easily find the result. So in this, in these expressions, yeah.
So among the so many scalars in the supergravity, so which one is identified with the influence?
Yeah, that's the next story. Yeah. So how can we okay, how can we realize the single field inflation? Yeah, the strategy is going to be to make the other scalars to be much heavier than the Hubble mass. That's the point. So in this case, our proposal can produce some special potential of the other scalar field. So this is the one. Actually, from the relations, actually we can extract the mass terms of the scalar field. And since now this potential has the inflationary energy scale, so which means that the corresponding mass scale must be Hubble scale. So this is the how things works. So in this case, actually, there's a motivation of the choice of the Kähler potential and superpotential. We choose the Kähler potential from the string theory. The Kähler potential will come from the modulus field, and the superpotential can be obtained from some Gaussian condensation or non-perturbative part, the non-perturbative effect about the deep brain actions. And then since we were interested in realizing the standard model, so actually we started with some minimal supersymmetric standard model superpotential. So by combining these things and then after length calculations, we found that some right SM fermions and some Hubble mass scale Higgs-Zenos and Hubble scale the other charged Higgs-Zenos and the other masses of the superpatrons of the scalars. So in protons, superpatrons also can have the Hubble scale mass. Actually, the Hubble scale mass is very heavy because the Hubble scale mass is around 10 to the minus 5 and Planck, which means that 10 to the 13 GeV. This is very, very massive compared to the user particles. So the last one, the take-home is this. The physical action of four-dimensional anti-coherence conformal supergravity can be considered as a framework for exploring phenomenology of all the particles and their interactions in a unified way. So we can study some particle phenomena like scattering amplitude and particle decays, and cosmological phenomena like inflation and some reheating dynamics and primordial black holes formation mechanism, or the generation of non-Gaussianity during inflation. And also, we may study some astrophysical phenomena like stochastic gravitational waves that can be generated from particle decays or the others, or like primordial black hole evaporation mechanism. And then this is the last point. Usually there's some GR community who study the classical gravity theories. But as we can see in the previous sections, actually in conformal supergravity, the scalar field dynamics is very intertwined with the fermionic dynamics from the effector field theory perspective. So actually, you may see that some gravity theory is not consistent in the sense that the cutoff scale of the theory is not comparable with some fermionic dynamics or the scalar field dynamics. So for example, imagine that you wanna describe inflation dynamics. Then you have to realize some power scale potential, something like that, some F phi. But actually, the scalar potential is associated with some recent coefficient of the non-renormalizable fermionic interaction terms, which means that we have to consider the effective field theory constraint, which means that these guys may get some constraint. So if the constraint tell you that something like 10 to the minus 20, something like that, then this result is not comparable with the intended scenario. You see, actually, this is the 10 to the 10 scale, but this is the 10 to the minus 20. So this is contradiction between them. So in that way, you can determine whether your theory may be consistent in describing the scenario you would like to study. in the conformal supergravity. Yeah. Thank you.
Very simple question.
Yeah.
Where is cosmology in your presentation? I know. But I could not see
Big guy potential.
this one.
Yeah, this one. So actually I start with
To make it a potato and the from
yeah, I actually my PhD advisor and I start with some KKLT type supergravity. This is the prototype. Yeah, and actually the KKLT model predicted this kind of potential, but this is not Stravinsky type. There's a bomb here, and this is the metastable vacuum. Yeah. So to overcome these problems in string theory, I introduced some new proposal, which was studied by some Antoniadis, and then I found that the pre-type of KKLT model can go to the usual Stravinsky type potential, thanks to the new Fi term. The Fi is some Phi Heliopolis terms. Yes. So yeah, it's possible to realize the single field inflation by using this proposal.
So have you solved the pre-qualification?
Oh,
Pre-qualification to show the behavior of the
yeah. Yes. So yeah, with respect to
necessary to P3 game in your model?
no. This the user proposal was using some D3 brain non-perturbative actions, but in this case, in our case, just we choose to throw up the D3 brain option, but instead we introduced some new Phi Heliopolis terms. Actually, the Fi term, the standard Fi term, can be obtained only by imposing some gauged R symmetry. But the gauged R symmetry can strongly constrain the form of superpotential in general, which means that we don't have much freedom in choosing superpotential. But the new Fi term can be defined without gauged R symmetry.
So when you're choosing the new Fi terms,
Mhm.
it's just one. This is only one term, so you choose.
Yeah, one term. This is the new Fi term proposal. Yeah.
And also you may choose some superior coefficient.
Yes.
So you something choose to make the
Yes. Yeah. Yes, that's right. So just starting with this proposal, we could realize the Stravinsky type inflation in the single directions, because in this model, the other scalars are heavier than the Hubble mass. So actually, they will not contribute to inflation.
How natural it is. How natural is this?
Our nature,
Natural.
natural.
So do you have to tune the parameter?
The tuning will happen when we match the energy scale of the inflations. That's the thing. Yeah.
And also in the first part of your slide, you show the scalar ratio of the graph. In your case, how about F1? Scalar tensor.
Yeah. The slower parameters epsilon and eta can be much less than 1 during inflation, and also the tensor to scalar ratio can be very close to the observed value. So
That was that.
yeah, because the Stravinsky type potential will give you almost the same value. Yeah.
Could you show the results for the scalar tensor ratio?
The
potential.
Did you find NS?
Yeah.
Calculate NS?
Yeah.
So could you show?
So yeah, this is the this is the NS.
Your results. Your point is real in your results.
Yeah, we got around here.
You mean that you can manage the number of the parameter, that kind of thing. So you can limit that one.
If you compute the Stravinsky type potential, then you will get some value around here always.
In your case.
In our case too. Yeah.
So when you considering higher order terms of the Riemann, which is scalar, then the Stravinsky model is very difficult because it truncate the other terms and just only keep the I still. So if some theory from the something upper levels, then Stravinsky model is a very particular or very special model. It's not natural.
Yes.
In your case, if your case is just going to the Stravinsky model, then I guess that you think many things you take them value by hand.
Yeah, that's true. But yeah, our model has some parameters, and all the parameters will be determined by the condition. This is only the constraint I use. Then all the corresponding Schroeder parameters and S can be the intended values. Yeah, this is natural in supergravity information scenario. Yeah, this is the sum thanks to the predicted form of the supergravity scalar potential.
So H is input. H is a 10 to 14 GB or something. So you gave that.
The H?
Yeah.
The Hubble, yeah.
Yeah, input.
Yeah, input. Oh, yeah, 10 to the -5 Planck.
Yeah, okay, so that's basically.
Yeah, during inflation.
Yeah, because of the, H determines the tensor scale ratio. But,
yeah.
Nice bound.
I mean, so to arrive at your model, I guess you cut many precise you can.
Yeah, so that's the input, and maybe this is output.
Yeah.
From your starting period. To arrive at the cosmology, your result. I guess that you did many cut by your hand.
Not many, because as you can see, actually,
You have a lot of degrees of freedom.
Yeah.
Eventually, you use 1% of your model. That's the issue.
What about the scalar potential? What form of the scalar potential? Can you see?
the scalar potential,
Scalar.
scalar potential. Just I will. The scalar potential is the -3 ln e plus t bar -3 and phi and xi. Or this is the Kähler potential. The superpotential is gonna be
What's the function of phi?
Hmm?
Phi is a function of,
a general function of the complex scalar field.
yeah, but what's the actual function? Phi, so you choose a specific one, or
The phi one.
is it canonical or no?
Yeah. So we consider the canonical form, something like this. Yeah.
And I is just one.
No, the meta field. Actually, we can consider any number of meta field.
Yeah, but in your case, how many?
Just a general number. Yeah. Just it can be any.
No. In your model,
Yeah.
it runs from 1 to.
Yeah. It depends on the minimal supersymmetry standard model.
Yeah, but maybe MSSM doesn't contribute to your theory, right?
No. I constructed the most general.
It's okay.
Yeah.
Now, what's the result?
Yeah. The imperaton is this guy.
Okay.
Yeah, T. This is the modulus field motivated by string theory. Yeah. So imperaton can come from here, and then the meta fields come from these general canonical functions. Yeah, and then this. And this is the superpotential terms in hidden for the hidden sector, and the observer sector will be just the MSSM. So this is the full proposal of my model.
Yeah, but MSSM doesn't contribute to that equation.
Yeah. Just this will contribute in the reheating error. Yeah. So for the inflation, actually the imperaton is this.
Yeah, but what's the coupling between the imperaton and the MSSM? You need
Because from the Kähler potential metric. Yeah, Kähler metric. Yeah.
So you can get some connection between the two in the sense that
Yeah.
once you fix the model to explain the inflation,
Mhm.
then you have some prediction for the other set. You know, you have this free model that
Mhm.
allows to find some connection
Mhm.
between the visible part
Mhm.
and the inflation.
Yeah. So it actually the two different sectors can interact via the gravity-mediated supersymmetry breaking. Yeah, that's the mechanism.
But this is another. So you have to specify the certain.
I think that we just spent too much time, so maybe it's good to spring here and we can discuss more.
Okay.